IB ESS Ecosystems and Ecology 2, Part 6, is the first of two parts on biomes. This movie will introduce biomes and talk about their distribution as a function of a specific atmospheric circulation pattern known as the Tri-Cellular model. The significant idea is that climate determines the type of biome in a given area, although individual ecosystems may vary due to many local abiotic and biotic factors. Here is the outline for the entire Ecosystems and Ecology unit in the IB ESS syllabus. This is topic 2 in the IB ESS syllabus. Use this outline to find the part you need. This movie has its focus here. Here's a definition of a biome, or maybe yet a description of what a biome is. Biomes are regions of the earth inhabited by certain types of life, especially vegetation, a collection of ecosystems sharing similar climatic conditions, grouped into 5 major classes: aquatic, forest, grassland, desert, and tundra. Biome is a collection of ecosystems sharing similar climatic conditions, regions of the earth inhabited by certain types of life, especially vegetation. In this diagram we can see latitude lines, the equator, 30 degrees north of the equator, 30 degrees south of the equator. The poles are located 90 degrees north and 90 degrees south. These are the latitude lines. Now notice equatorial forests in dark green are located in large patches along the equator. Deserts in yellow are located in large patches, approximately 30 degrees north and 30 degrees south of the equator. Taiga in light blue, located across northern stretches of Canada, Scandinavia, and Russia, while tundra in blue across the polar regions of the world. Now, as a note, something to keep in mind, notice that not all equatorial regions have forest, or that deserts are not all uniformly found at 30 degrees north or 30 degrees south of the equator. Local geographic conditions strongly influence the presence or absence of certain biomes. The proximity to the ocean or the presence of mountain ranges strongly influence the local climate. I'll address this idea in the next movie. Here's another diagram of the world's biomes. This diagram does not have latitude lines. The equatorial line is approximately here. The world's tropical forests are generally found along the equator. The world's largest deserts are generally found 30 degrees north and 30 degrees south of the equator. Temperate forests are located between 40 and 60 degrees north or south latitude. Taiga forest is found above 60 degrees north latitude, and tundra is found near the poles. So here's an IB syllabus statement that's worthy of a full semester course. Explain the distribution of biomes based on global variation in precipitation and temperature using the Tri-Cellular model of atmospheric circulation. Before we can understand the distribution of biomes around the globe, we must step back and look, albeit superficially, at details around the energy budget of the Earth. So sit back, buckle your seatbelt, and follow along as I provide important background that will ultimately strengthen your understanding of biome distribution. In this diagram, you can see the annual mean temperature by latitude. Notice that tropical regions here are warmer on average than polar regions. Equatorial regions are, on average, the warmest. Now, this might seem obvious to you, but why does this pattern exist? Stay tuned. Here's a diagram that displays the average daily solar radiation at the surface of the Earth. Like the diagram in the last slide, this slide clearly displays differences in the amount of radiation across the globe. Now, why is this? Average radiation, the subject of this slide, is not exactly the same as average temperature, the subject of the last slide. But the amount of solar radiation does influence the temperature at the Earth's surface. But notice on this diagram, different from the last one, that regions directly on the equator receive a bit less surface radiation than regions 30 degrees north or 30 degrees south of the equator. Cloud cover in the equatorial regions reduce the radiation directly at the surface. There are no clouds over the deserts, so the quantity of radiation at the surface there is high. But big picture, notice that there is an uneven distribution of solar radiation across the globe. Now, why is this? The uneven distribution of solar radiation across the globe, thus the uneven temperature distribution, is curious given that as a system, the Earth has an equal in, equal out relationship with the universe. The amount of energy arriving as high-quality sunlight is equal to the amount of energy radiated back to the universe as heat. So, energy in equals energy out, but within the system, there is uneven distribution. That's interesting. Pay close attention as we move forward. The explanation for the uneven distribution of energy on Earth by latitude lies in the angle of solar radiation. The angle of solar rays as they approach a spherical Earth varies by latitude. Yes, the spherical shape of the Earth is important here. At the equator, solar rays are arriving as close to a 90-degree angle as possible, but nearer to the poles, the rays arrive at a more oblique angle. The radiation arriving at the equator is spread across an area outlined by this circle, while the energy arriving nearer to the pole is spread across an oval. Energy per area is more at the equator than near to the pole. Equatorial regions are warmer than polar regions due to the higher energy per unit area. Here you can see the same effect. Solar energy arriving at an angle of 90 degrees is spread over a smaller area, while energy arriving at a more oblique angle is spread over a larger area. Energy per area is greater whenever the angle of solar radiation is closer to 90 degrees. Once again, compare the area here and here. The area receiving insolation near the equator is smaller than the area receiving insolation near the poles. Energy per area is greater at E than at P. And one more idea to the mix. Solar energy arriving to polar regions is less likely to be absorbed because of ice and snow that would reflect it. Also, if you imagine a layer of atmosphere approximately here, the length of the radiation path through the atmosphere is less at the equator than it is at the pole. So less solar radiation is removed by the atmosphere at the equator. More energy reaches the Earth's surface nearer to the equator than at the pole. Nearer to the pole, the length of the radiation path through the atmosphere is more, so more radiation is removed by the atmosphere, thus less energy reaches the Earth's surface at the pole. So energy arriving to the Earth's system is equal to the energy leaving the Earth's system. But within the system, there are locations that receive more than other locations. Let's take a different look at this relationship. This graph displays energy absorbed by the surface of the Earth by latitude, as well as energy radiated by the surface of the Earth by latitude. 0-degree latitude is the equator, and the poles are here and here at 90 degrees. Notice that the equator has more in than out, a surplus, if you will, while the poles have more out than in, a deficit. As a result of the uneven spatial distribution of energy, energy is moved from regions of surplus, the tropics, to regions of deficit, the poles. Winds and ocean currents serve the role of transferring energy from tropical regions to polar regions. At this point, I've provided the basic explanation for why the tropics are warmer on average than the poles. But this doesn't explain seasonal temperature change. If the Earth's rotational axis was at 90 degrees relative to the sun, tropics would be warm, polar regions cool, and that's it. End of story. But in fact, the Earth's rotational axis is 23.5 degrees off from 90. And this adds another chapter to our explanation of the Earth's energy budget. So let me extend the detail around the Earth's energy budget just a bit by asking another question. Why are there seasons? Why is December in the northern hemisphere colder than June? Why is December in the southern hemisphere warmer than June? Seasonal variation in radiation, and thus temperature, results from the Earth's tilt in its rotational axis. In June, the northern hemisphere is tilted toward the sun, thus changing where on Earth solar radiation arrives at a 90-degree angle. In June, the Tropic of Cancer, 23.5 degrees north of the equator, is the latitude where solar radiation is arriving at a 90-degree angle. As well, in June, locations north of the Tropic of Cancer are receiving solar radiation at the highest possible angle of any time in the year for that location. Notice that the North Pole is receiving light, and if you're thinking clearly, as the Earth rotates through one day, the North Pole receives light all day, never going into the shadow of darkness. In December, when the Earth has moved to the opposite side of the Sun in its yearly orbit of the Sun, the southern hemisphere is tilted toward the Sun, such that the Tropic of Capricorn is receiving solar radiation at 90 degrees, and latitudes toward the South Pole are receiving solar radiation at the highest angles of any time in the year for that location. Notice that the South Pole is receiving light all day long. Notice that the North Pole is in complete darkness through entire days. In the course of its orbit around the Sun, there are two times in the year, March and September, when the Earth's rotational axis is 90 degrees relative to the Sun. These times are known as the equinox. The equator is receiving solar radiation at a 90-degree angle. On these days each year, each location on Earth receives 12 hours of light and 12 hours of dark. Here's a diagram that puts you in space looking down on the Earth, orbiting the Sun, looking down on the northern hemisphere of the Earth. In June, the northern hemisphere is tilted toward the Sun, thus the polar region is receiving full days of sun, while in December, the north polar region is tilted away from the Sun, resulting in entire days of darkness. In this diagram, you can see why the equator receives solar radiation at 90 degrees in March and September, and day lengths are equal all over the world on the equinox. This is a very interesting graph that displays energy absorbed by latitude across the seasons of the year in the northern hemisphere. Notice the equator, 0 degrees latitude, has a high quantity of solar radiation absorbed throughout the year with just slight fluctuations, although the highest levels received by the equator happen in March and in September. Notice at high latitudes near the North Pole, they've got high quantities of solar radiation in May, June, and July, as high or maybe just a bit higher than at the equator. Remember, polar regions are bathed in light for many, many hours of the day in May, June, and July. But look at the solar radiation input at the poles in November, December, and January, February. Very little, if any. Here's a graph that displays solar energy absorbed by month in the northern hemisphere at 3 latitudes, the equator at 40 degrees north latitude and 80 degrees north latitude. Notice the energy input at the equator remains high with slight fluctuations throughout the year. Solar radiation at the poles varies dramatically from 0 during the winter months to high values during the summer months, even exceeding radiation absorbed at the equator. Keep in mind the unit. This is per day on a daily basis. In June and July, the poles are receiving nearly 24 hours of sunshine, and that's why the energy absorbed per day exceeds equatorial values, where half the day is spent in nightfall. So that brings me back to the biomes of the world, and if nothing else, you have some understanding of warm temperatures at the equator and cold temperatures in polar regions, with everything in between. Biomes are regions of the Earth inhabited by certain types of life, especially vegetation. They are a collection of ecosystems sharing similar climatic conditions and are best understood to be determined by precipitation and temperature. These two abiotic influences are most important in determining the location of a biome. Warm and wet results in tropical forests. Dry conditions results in deserts at any latitude. Cold, wet conditions results in coniferous forests known as the taiga biome. And extreme cold in combination with low light conditions on a yearly basis results in the tundra. So I've come back to this IB syllabus statement, explain the distribution of biomes based on global variation in precipitation and temperature, using the tri-cellular model of atmospheric circulation. In the slides to follow, I will introduce you to the tri-cellular model with the hope of explaining the presence of rainforests near the equator and the presence of deserts 30 degrees north and south of the equator. In this first diagram of the tri-cellular model of atmospheric circulation, we can see three large cells of air movement from the equator to the pole. The same set of three cells exists both north and south of the equator. The first cell is the largest, it's most powerful, known as the Hadley cell, and it circulates this way. Air rises at the equator and falls about 30 degrees north or south of the equator. The second cell circulates like this, and the third cell circulates as we can see here. The equator is a region of rising air, and here we can see air sinking or descending toward Earth. And here air is rising, and here it is sinking. The arrows of air movement running parallel to the Earth's surface would be known as surface winds. We live here at the surface, and these flows we would experience as wind. Here's an image that shows the first large cell of atmospheric circulation, the Hadley cell, on either side of the equator. Just as in the last slide, air rises over the equator. This can be explained by the high solar radiation at the equator, thus high temperatures, and warm air rises due to its lower density. After the air rises to altitude, it cools at elevations well above the Earth's surface. Temperatures are lower at high altitude, and you experience this when you climb a mountain. The details of temperature change through the atmosphere will be left for another day. As the air rises, the air cools. Water vapor carried with the air also cools and condenses, gas to liquid. Cold air does not hold as much water vapor as warm air, so at altitude, water vapor condenses. As the vapor condenses to liquid, the liquid falls back to Earth as precipitation. Thus, equatorial regions have rainforests because tropical regions experience a warm, wet climate. Then, at elevation, high above the Earth's surface, the cold air, now dense and empty of water, begins its descent back to Earth. As the already dry air sinks, it warms. It warms because it is approaching the Earth's surface where temperatures are warmer. As the air warms, water is evaporated, liquid to gas, because warm air holds more water as vapor than cold air. Thus, the dry air sinks, it warms, evaporating water, resulting in no clouds, resulting in deserts. The world's large deserts are 30 degrees north and south of the equator, where air descends and sinks as part of the Hadley cell. Rising air at the equator causes a low pressure zone. Air flows along the surface from north to south and from south toward the equator to complete the circulation of the cell. In this slide, the equatorial region is located here, and air rises because this is the region that receives the highest insolation. Thus, air, on average, is most warm here, and warm air rises due to its lower density. This is a region of low pressure because air is rising, moving away from the surface. The rising air cools at altitude. Water vapor condenses and clouds form, and clouds will result in rainfall in this region. The cold, dry air circulates north and south and begins to sink because it's cold and of higher density. The sinking air, already having left its water behind, warms as it sinks. This is a region of high pressure. The sinking, warming air holds more vapor. In other words, warm air is evaporative. There's no condensation, no clouds, dry conditions, a desert in this region. Lastly, air flows from regions of high pressure to low pressure, from regions north and south of the equator to the equator. The region where the air converges is known as the Intertropical Convergence Zone, the ITCZ. Now here we have all three cells. The first is here, the Hadley cell. The second is here, and the third atmospheric circulation is here. Air is rising here, sinking here, rising here, and sinking here. Wherever air is rising, there will be rainfall. Wherever air is sinking, there will be sunshine, no clouds, dry conditions. Tropical regions have high rainfall due to rising air and due to the warm conditions related to the angle at which solar radiation reaches the Earth's surface. High pressure regions here and here, approximately 30 degrees north and 30 degrees south of the equator, are dry due to air descending from altitude, warming as it descends, holding more vapor, evaporating liquid water, resulting in no clouds, desert conditions. Rising air between 50 and 60 degrees latitude results in rainfall, temperate forests in this region. Sinking air in polar regions results in little rainfall. Any precipitation that does fall freezes as snow or ice, tundra. The air flowing along the surface, let's say toward the ITCZ, is turned or rotated, as you can see here and here. But let's not complicate things by diving into this phenomenon known as the Coriolis force. If we spent a bit of time looking at winds and the Coriolis force, we could better understand prevailing winds. The actual pattern of air movement is more complicated than meets the eye, but the Tri-Cellular model does assist us in explaining the distribution of biomes that we see when we study a map of the Earth. Remember that winds and oceans serve to redistribute heat, given the uneven distribution of energy, uneven due to the angle of solar radiation on a spherically shaped Earth. In case you missed any of the cause and effect relationships of air temperature and water, let me try one more time. Warm air evaporates water. Air rises when it's warm because it's less dense. Rising air carries water vapor, not visible to the eye, to altitude. At altitude, the air cools. Cold air holds less water vapor, so vapor condenses, forming clouds. Clouds, liquid, will result in precipitation here. Here is another image of the Tri-Cellular model of atmospheric circulation. If you look carefully, you can see the circulation patterns of each of the three cells. The author of this diagram makes a mistake with the circulation over the poles. Air should be sinking here, not rising. Now, the Hadley cell is the most energetically powerful of the three cells. This makes sense. The tropical regions have an energy surplus relative to the polar regions. Here again, we can see surface winds being turned by the Coriolis force. Average solar radiation and temperature are influenced by latitude, as I've emphasized over the last 20 slides or more. But latitude alone does not determine local climate. Local climate is also influenced by local geography. For example, a location's altitude above sea level would influence its temperature. Its proximity to large bodies of water would influence temperature because water has a high specific heat, or currents can transfer warm or cold air near to a location. As well, some locations have prevailing winds, also transferring warm or cold air, redistributing heat around the globe. Mount Kilimanjaro nearly reaches 6,000 meters, 20,000 feet, and it is located almost directly on the equator. Despite being on the equator, you will not find tropical forests at Kilimanjaro's summit. The summit has permanent snowfields. Mountains result in unique rainfall patterns. Prevailing winds on the windward side will rise due to the physical presence of the mountain. Rising air will cool at elevation. Water vapor will condense, resulting in rainfall. Rainfall on the windward side. Air flows over the range and then the cold air sinks, warming as it sinks, resulting in dry conditions on the leeward side. On the leeward side of the mountains, desert conditions exist. The region on the leeward side of the mountain is known to be in the rain shadow of the mountains. Again, mountains result in wet conditions on the windward side and dry conditions on the leeward side. The leeward side of the mountain is in the rain shadow. At any given latitude, the windward side would be wetter and the leeward side would be drier than expected. This region is a desert. The Atacama Desert of Peru, one of the driest deserts on Earth, is in the rain shadow of the Andes, despite being located within the tropics. Morocco, seen here, is located 30 degrees north latitude, at the same latitude as the Sahara Desert. But due to its proximity to the Atlantic Ocean, it receives more rainfall than interior locations, thus the vegetation that's clearly evident. Notice the Atlas Mountains, which rise up over 4,000 meters. Considering the latitude of these mountains, notice the snowcaps. Latitude, as well as local geography, influence the local climate. Proximity to bodies of water influence the local climate, including causing more moderate temperatures, warmer in the winter and cooler in the summer. This diagram shows mean surface temperatures in January and July, and there are many points to be made here, but let me make one, and that is the influence of ocean currents on local climate. Let's follow the 0-degree line from west to east along here. Notice how far north this 0 degrees C line goes. In January, the temperature here at 0 degrees C is far warmer than you might imagine, given the latitude and the month. This results from the Gulf Stream, a warm ocean current transferring warm water from tropical latitudes to polar latitudes. Let's look at this 20-degree C line here. Notice that this relatively cold temperature extends north along the coast of Peru. The cold temperature here within the tropics results from the cold Humboldt current that transfers cold Antarctic water toward the tropics. This IB syllabus statement will be the focus of the next movie, and it's the last of this series. However, you should be able to talk about general aspects of biome distribution. Explain the distribution, structure, and relative productivity of tropical rainforests, deserts, grasslands, temperate forests, and tundra. Refer to prevailing climate and limiting factors of each biome listed. As well, you should gain familiarity with aquatic biomes. Here's a nice diagram that shows the location of biomes based on temperature and precipitation. Let's start with deserts. Deserts are located in regions with low precipitation, but experience a wide range of temperature. Tropical forests are located in regions with warm temperatures, but tropical forests vary with respect to the amount of rainfall. Now notice that tundra is located in regions with cold temperatures and low rainfall. Now the temperate deciduous biome is located in regions with warmer temperatures than the taiga biome on average. Both biomes experience relatively wide-ranging temperatures and precipitation. Here's another diagram that displays biomes according to precipitation and temperature, the two most important abiotic factors in determining local climate. The tropical forest biome is located in regions that receive high precipitation and warm temperatures. The tundra biome is located in regions that receive low precipitation and low temperatures. I'll let you study this slide more on your own. Precipitation and temperature are the two most important abiotic factors influencing local climate. As a result, some biomes are more productive than others. To compare biome productivity, we must use the middle column, displaying NPP in grams per meter square per year. Comparing biome productivity can only be done on a unit area basis. Rainforests are very productive because of warm, wet conditions. Deserts are very unproductive because of the lack of precipitation. Temperate forests have an intermediate level of productivity between that of deserts and rainforests. And that brings us to the end of ESS Ecosystems and Ecology 2, Part 6. The last movie of this series, Part 7, will take a closer look at specific biomes, further addressing productivity, structure, and distribution.